Right, let's crack on with this question. So this is all about the enthalpy change of combustion of an alcohol, in our case, ethanol. It's a calorimetry experiment, so have a look on the right. That's how you would have that set up. And it's good to be able to picture these experiments when you're trying to figure out a question. So enthalpy change, what is that even all about? The amount of heat energy that is taken in or given out in a chemical reaction. That's all that is. We're not able to measure enthalpy, but we are able to measure enthalpy change. So as we said, this is calorimetry. So as we've said, this is a technique called calorimetry. The idea is that the heat given out in this combustion reaction, okay, we're giving off heat by burning our alcohol, by burning our ethanol, is then used, the heat that's given off from that is then used to heat another substance. In our case, this water. We're heating this water and we know the specific heat capacity of that water. That's very important. You have to know that. Otherwise, you can't do this. And we do know that we're given the specific heat capacity of water as 4.18. So now let's answer the question. We know that we'll be using our formula. Q equals mc delta T. This will help us work out the amount of energy, of heat energy, that is supplied to the water by the burning of the alcohol. Because we're focusing on the water at the moment, we are inputting all our water values. What does that mean? It means that for our mass, we'll be using the 150 grams. Then we've got our specific heat capacity and our temperature change. That will be 45.7 minus 19.5 gives us 26.2 degrees Celsius. Does it matter that it's in Celsius? Should it be in Kelvin? No, it does not matter. Why? Because it's temperature change. Whatever unit it's in is going to be the same number. So we times that by 26.2 as well. What do we get? 16,400 joules. So again, note that we are using the mass of the water, not the mass of the ethanol, because it's the water that we are heating here. You might know that in order to work out delta H, we do our Q divided by our moles. Now this will be our moles of ethanol, yeah? The number of moles of ethanol that we are burning. So let's work out the number of moles of ethanol. Well, moles is mass over mR. So what's the mass of ethanol burnt? Well, that would be 121.67 minus 120.62 gives us 1.05 grams. So that's our mass. We're dividing it by the mR. The molar mass of ethanol is 46.08. Make sure to use the correct values from the data booklet. That gives us 0.0228 mole. Okay, those are the moles of the ethanol burnt. So now we can go back to this. Delta H is 16,400 joules divided by 0.0228. That will give you 721,000 joules per mole. Some last things here. We tend to use kilojoules instead, so we're going to be converting this to 721 kilojoules per mole. Are we done? Are we done? Look like we're done, but we're not. Why? Because this is a combustion reaction. Combustion. That means we need a big minus here. Do not forget this minus. In fact, if it helps you, you can put the minus in front of the mass in your equation. Okay? Put it in your equation if you think you're going to forget it. You will not get full marks unless you have that minus for this type of question. Now we are done. Your answer should be minus 1080 kilojoules per mole. But now they're telling us that the actual value is a different one, minus 2010 kilojoules per mole. How do we account for these differences? What are some of the flaws, some of the systematic errors in our setup, in our experimental setup? Well, number one on your list should be heat loss to the surroundings. We know that of the heat energy released when our alcohol burns, only some of it goes into heating the water. The rest goes into heating the copper can, the surrounding air. So actually, something that we could do to improve this is to determine the specific heat capacity of the can and take that into account when doing the calculation, right? We can also insulate the can so that less heat is lost to the surroundings using some sort of shield to reduce convection currents around the experiment. Another major problem is incomplete combustion. This is the combustion of the alcohol. If we don't have enough of a supply of oxygen, then some of the alcohol can burn to produce carbon monoxide and carbon as well as water. Yeah, those are the products of incomplete combustion. So these are the things that you can talk about to explain the difference between the literature value and the experimental value. I hope you have found this useful. If you did not get the right answer for the second question, have another look at the steps that we went through in the first example. Try it again and I'm sure you'll get it. You've got this.